Let's take a quick look at the architecture of Spark. Remember, fundamentally, we're trying to write a program that does some data analysis. And that's, in this diagram, the thing we call the Spark client. That's a program that maybe we've written in Java or Scala or Python. Those are the three most common languages that does the actual computation. Inside the Spark client is a component we call the driver, which is code that's interacting with the Spark context. Now, the Spark context is an actual object in one of those languages. For example, if you're writing in Scala or you're writing in Java, there's a class called Spark context with a well-documented interface, and you directly program that interface to create pieces of data, to import data, export data, transform it, and run computations on it. And a lot of learning Spark programming involves learning the APIs in the Spark context and the objects related to it. So that driver, which is potentially a complex piece of code, has to get resources to do the computation. It does that by connecting to a special node in the Spark cluster called the master. The master is a fairly lightweight process. Clients, what they do is they request a certain number of cores and a certain amount of memory to do some computation. So the master will ask workers, according to the number of cores and the amount of memory they have available, to allocate executors. Once those workers have allocated executors, the master is in a sense out of the picture. Those executors then communicate directly with the Spark driver. And the Spark driver gives them their computational work to do, importing data, exporting, transforming, running some action or some aggregate computation over data. All of that communication happens between driver and executor. And when results are returned, those go from executor back to the driver. The master is not in the loop anymore at that point. Fundamental to Spark computation is a directed acyclic graph of operations. We just call that a DAG, D-A-G, for directed acyclic graph. Now, this is, again, a thing we will dig into in more detail later. But to think of it in simple terms, you might imagine you start with some source data, you perform one or two maybe filtering operations on it, and then maybe compute an average of some value in that data. You've already defined a sequence of operations where one depends on the next. In a complex job, that sequence and really that network of operations forms a more interesting graph. Spark computes that graph and is aware of that graph. Sometimes, as a developer using Spark, you don't even need to be directly aware that the Spark driver is computing that graph for you. The driver will break that sequence of computations down into one or more jobs, and each job will be composed of stages. Each stage will get implemented by one or more tasks. And it's this task level that the driver finally decomposes the work down to where computation can happen. Those tasks are then handed off to those executors that we had allocated just a minute ago. The work is done by those executors, and the results can then be obtained later on by the driver when it needs them. You can see how this architecture lends itself pretty well to horizontal scale. Things get decomposed into these relatively simple tasks from a potentially complex series of operations that we define as developers, and those tasks then get parceled out to various nodes in the cluster. How many nodes, we don't know. We could have a small number, we could have a large number if we have a lot of work to do. The architecture itself, it doesn't really care how big the cluster is, which is definitely an attribute that we'd like. Now we're going to assume that you already know the basics of Cassandra. If you don't, there are resources elsewhere here on DataStax Academy that you'll be able to learn the fundamentals of the architecture. But remember, it's a peer-to-peer database with fault tolerance baked in, and there is the consistent hashing mechanism that you can see illustrated in the slide that Cassandra uses to distribute data among nodes in the ring. So all of the data ought to be, in a properly designed Cassandra schema, evenly distributed among the nodes. This picture shows 3, which is kind of a minimum viable Cassandra cluster in some sense. Of course, there could be dozens or even hundreds of nodes, and all the principles are the same. Importantly, you also have the ability for client applications to connect to arbitrary nodes. We saw a minute ago how the Spark client connects to the Spark cluster. In the case of client applications writing data to Cassandra and reading it from Cassandra, they can connect to any node they want, and the cluster itself maintains the distribution protocol. When Spark is running on Cassandra, as in the case of the DSE analytics feature, you can see that every node in the Cassandra cluster also has the potential to function as a Spark node. One of them will be elected as the Spark master, the others will be Spark workers. Now, the way this works in practice is sometimes not every node in a cluster is given analytics duties. Sometimes that's partitioned. We'll look later at how that happens. But in principle, every node is available to do that same work. And while Spark is electing a master, because that's important to Spark's architecture, remember there's no master node or no distinguished node of any kind in Cassandra, and using Spark on top of Cassandra doesn't change that fact. Since Cassandra has multi-data center functionality baked into it, we can use that to partition analytics workloads. The actual tuning that the ops people are going to have to do on the servers themselves, the ones that run the analytics workload, the ones that run the transactional workload, those happen to be different. Sometimes there are trade-offs that work at cross purposes. So you might want to optimize a certain set of nodes in your cluster to handle the transactional workload well, and another set to handle the analytics workload well. In Cassandra, we'll set up multiple data centers. Now, they don't have to be actually geographically diverse data centers. They can simply be a set of 5 nodes and a set of 10 nodes that are all in the same rack. But one of those data centers can be given Spark responsibilities and the other purely Cassandra data storage responsibilities. Cassandra will keep the 2 data centers consistent, and then we're able to optimize the analytics workload on the nodes that are running Spark.